Hello students, in this video we'll discuss the Gram-Schmidt procedure for orthogonalizing a set of vectors. Let's suppose we have vectors v1 through vk in Rn. I have k vectors in Rn, and we wish to find an orthonormal set phi 1 through phi k. Of course, this is an orthonormal set, so those phi 1 through phi k are orthonormal vectors, such that the span of v1 through vk is the same as the span of phi 1 through phi k. Okay. In particular, what this is saying if I give you a set of vectors which are sort of at tilts with respect to each other, that aren't at perfect right angles, I want to find a collection of vectors that has the same span, gives me the same overall collection of vectors in totality, but form perpendicular to with respect to each other, which makes computing the coefficients much simpler. Okay? And so the Gram-Schmidt procedure allows us to do this. So here's the Gram-Schmidt procedure. What does Gram-Schmidt say to do? It says define phi 1, I'm going to put a hat because I want those to be normal vectors, just to be v1 over the length of v1. Okay? Then the span of phi 1 is the same as the span of v1, right? This implies that the span of phi 1, just the phi 1 hat, is the span of v1 because they're proportional to each other. Okay? Now I need to construct phi 2. How are we going to do that? Well, I'm going to take v2 and I'm going to project it onto the phi 1, right? So let's do this. Let's first define u2 is going to be what vector over here? u2 is going to be the vector v2. Okay? So in other words, it has to contain part of v2 to be in the span. And then minus the projection, minus the orthogonal projection, the projection of v2 onto phi 1, v2 onto phi 1 hat, right? And let's recall what the formula for projection is, right? This is going to be v2 minus v2 dot what? Dot phi 1 hat over phi 1 hat dot phi 1 hat, phi 1 hat, right? Now phi 1 is a unit vector, so this denominator is equal to 1. So this is exactly what? This is exactly equal to v2 minus v2 dot phi 1 hat, phi 1 hat. That's my u2, right? And then I'm going to find phi 2 hat to be u2 over the length of u2. Okay? Beautiful. Okay? Now, because this vector over here might not be a unit vector, so I just make it a unit vector. Easy enough, right? Okay, so now let's check what the properties of this u2 are, and thereby by scaling phi 2, right? So u2 is a what? u2 is a linear combination of v2 and phi 1, but phi 1 is in the span of v1, right? So if I look at the functions phi 1 and phi 2, the span of phi 1 and phi 2 definitely contain the span of v1, and now also what? And now it's a combination of v2 as well. So automatically we get what from this procedure? We get the span of v1 and v2 is the span of phi 1 hat and phi 2 hat. Great? Let's do the next step in the procedure, and then we'll see how to do it by induction, right? So what will u3 be? u3 is going to be v3 minus the projection of v3 onto phi 1 minus the projection of v3. Of course, by construction, we know that this what? We failed to mention that by construction, this v2 is automatically what? This v2 is automatically perpendicular to this phi 1, right? Because if I dot them, I'm going to get 0 automatically, right? Okay? Good. In fact, we can see that, right? If, for example, I did v2 dot phi 1, what would happen over here? v2 dot phi 1 is going to be what? Is going to be, that's v2 dot phi 1, v2 dot phi 1, and that's going to be a 1, so it's going to cancel and give me 0, right? Minus the projection of onto phi 2 of v3, right? And so now, of course, this formula will simplify for us because it's going to be very, very nice. And then I'll normalize this U3, right? And that won't change the orthogonality properties at all, right? So it's going to be V3 minus what? Minus V3 dot phi 1 hat in the direction of phi 1 hat minus V3 dot phi 2 hat in the direction of phi 2 hat. Okay? Now, what can I say about this vector? If I dot this vector, for example, say, with a phi 1, I'll get 0 because I'll have v3 dot phi 1 and minus v3 dot phi 1. If I dot this vector with phi 2, I'll have v3 dot phi 2, and then v3 dot phi 2 over here will cancel out. So this vector over here, u3, is perpendicular to both phi 1 and phi 2. And I know that if I normalize this, if I look at phi 3 hat, it's going to be what? It's going to be u3 over the length of u3. Then the span condition is the same, right? Then the span of v1, v2, v3 is equal to the span of phi 1 hat, phi 2 hat, phi 3 hat. Trivially, okay? And of course, that makes it normal, right? So in other words, in general, what we do? In general, we're going to subtract up to that level, right? So if I get up to 5k, what will the phi k be? The last one over here, so phi k. So uk will be vk minus the sum. J goes from 1 to k minus 1, the projection onto phi j of vk. So I sum up all those projections over there. So I subsequently project all these things, and then define phi k hat to be equal to what? I define phi k hat to be uk over the length of uk. And by construction, if I dot this uk with any of the phi j's over here, I'm going to get exactly what? I'm going to get vk, and then I'm going to get vk dot phi j. So this is definitely orthogonal. So that's a trivial check to say that this uk is perpendicular to all of the phi j's for j going from 1 to k minus 1. So that I've constructed now, so the set by construction, so phi 1 hat, phi k hat is an orthonormal set. And the span is the same, right? And this condition is true. So it's just the Gram-Schmidt algorithm produces this set over here. So let's see a quick example of doing this, right? So for example, if I give you these three vectors over here, let's go to our vectors. Example. If I look at the vectors 1, 0, 0, I'm going to choose vectors that are sort of simple to save us some space and just to illustrate the basic point over here, and then put a 1 over here. That's going to be a 1. Got greedy, I want to put a 0 there. Now we can imagine what Gram-Schmidt is going to do with this. Well, of course, the first vector, phi 1 hat, is just going to be v1 over its length. So the phi 1 in this case over here, so this is my v1, v2, and v3. Then my phi 1 hat is just going to be this e1, which is just v1. Great. Now what's phi 2? What's my u2 going to be? My u2 over here is going to be my v2, so 1, 1, 0. And then I'm going to dot what? I'm going to dot my v2 with my v1. So this v2 dot v1 is equal to 1. So I'm going to subtract off 1 over the length of my phi 1, which we know is equal to 1, in the direction of what? In the direction of phi 1, which is v1. So in the direction of 1, 0, 0. And that gives me what? That gives me 0, 1, 0. Oh, look, that's just e2 hat. Beautiful, right? So my u2 is e2 hat. So in other words, it generated e2. Now what is the final vector going to be? What's my u3 going to be? My u3 is going to be v3, which is 1, 1, 1, minus the projection of v3 onto the phi 2, right? So it's going to be the dot product of those things, right? So let's do it carefully. So we're going to have what? We're going to have the that's also my phi 2, right? Phi 2. Okay? So it's going to be minus the projection of this vector, so 1, 1, 1, dot what? Dot the phi 2, which is e2, 0, 1, 0, over 0, 1, 0, dot 0, 1, 0, in the direction of 0, 1, 0. And then the same thing with the 0, 1, 1, right? So that's going to be a minus 1, 1, 1, dot 1, 0, 0, over e1 hat dot e1 hat in the direction of e1 hat. Now check out what this thing is over here. This thing is equal to just 1 over here, so that's just e2 minus e1. So I have 1, 1, 1 minus e2 minus e1. That just gives me E3 hat, right? And so, of course, that's going to be my phi 3. And so if I take this vector over, these vectors over here, 1, 0, 0, 1, 1, 0, 1, 1, 1, and I apply Gram-Schmidt, I get E1, E2, and E3, and we know those are clearly an orthonormal set that has the same span as this collection V1, V2, and V3. Thank you very much.